Dalton's law of partial pressures. Till now, we talked about ideal gases and some of the laws that describe their behavior, such as Boyle's law and Charles' law. But until now, we have been examining the relationship between different variables using this formula PV equals nRT for an individual gas. So all of those laws like Boyle's law, Charles' law, and so on, they are for individual gases. Now, uh, we want to know if we take different gases and mix them together, what would be the total pressure and how those gases behave as well. So here is the rule. As long as the gases don't react with each other, they will apply the same pressure whether they are alone or they are in a mixture. And we call that pressure of that particular gas its partial pressure. So imagine we have oxygen with partial pressure of 0.4 atmosphere, and we add that to the nitrogen gas with partial pressure of 0.6 atmosphere. Now, to find the total pressure after mixing them together, we can simply add 0.4 atmosphere from hydrogen with zero point 0.6 atmosphere from nitrogen, which gives us overall 1 atmosphere. So the total pressure would be 1 atmosphere, and this is the Dalton's law. And that makes sense because pressure depends on the number of collisions with the sides of the container. The more particles of the gas you have, the more collisions you'll get and more pressure you have. So therefore the total pressure would be the sum of all the partial pressures of the components in the mixture, and this is how we present the Dalton's law. But don't forget the rule, because those gases should not react with each other and should act individually, because they are ideal gases. Now, how can we calculate the partial pressure? There are two ways to calculate partial pressure. One is when we know the number of moles of a gas in the container with known volume and temperature. So in this case, we can simply use the PV and RT formula. We know the temperature, volume, and number of moles. We can simply calculate the pressure. The second way is when we know the mole fraction of that gas and the total pressure. So in this case, we need to know the mole fraction and the total pressure. Now, what is mole fraction? So mole fraction is the ratio of the moles have a gas, a specific gas or component in relation to the total moles in the mixture. Now, imagine we have a container and we have different moles of component A and like 5 moles of component A and 3 moles of component B. To calculate the mole fraction for component A, we simply need to divide the number of mole of A, which equals to 5, by the total number of mole, which is 5 plus 3, 8, gives me 0.625. And we show that as XA, which is the mole fraction of component A in the mixture. To calculate the mole fraction of component B, you have two ways. One is dividing the number of mole of B by the total number of mole, which gives me 3 divided by 8, 0.375. Or we have another rule here, and that rule states that XA, mole fraction of A, plus mole fraction of B equals to 1. So you have the mole fraction of A, you can simply calculate mole fraction of B by 1 minus 0.625 gives you 0.375. Now, this is the way to calculate the mole fraction in the mixture. How can we calculate the partial pressure? To calculate the partial pressure, for example, for component A, we simply need to multiply its mole fraction by the total pressure. And that will give us the partial pressure of component A in that mixture. Now the application. A mixture of gases contains 0.170 moles of hydrogen, 0.230 moles of nitrogen, and 0.200 moles of neon. The total pressure of the mixture is 145 atmosphere. What is the partial pressure of nitrogen? So if you recall, to calculate the partial pressure of nitrogen, we need to multiply the mole fraction of nitrogen by the total pressure. If you look at the question, we have different number of moles of each components, so we can simply calculate the mole fraction of nitrogen from them, and we have the total pressure of 1.45 atmosphere. So the first step is to calculate the mole fraction of nitrogen, which is number of moles of nitrogen over the total number of mole. So nitrogen is 0.230 moles divided by 0.170 plus 0.230 equals 0, and the answer would be 383. So to calculate the partial pressure, we have the mole fraction of nitrogen 0.383 multiply atmosphere gives 0.556 atmosphere. Now let's talk about reactions that involve gases. As you can see in the workflow above, majority of the time you are given measurable quantity of the gas, either one of them or all of them, and you can simply from those components using the gas law you can get the number of moles of component A, and then from there you can use the balanced equation to get the number of moles of B, and from there again using the gas law, but for component B find the measurable quantities of the gas, what is asked in the question. Another important thing you should be careful about is when the question is asking about STP. So just as a reminder, STP was a condition of 1 atmosphere at 0 degrees Celsius or 273 Kelvin. Under these conditions, we can always use this equality that 1 mole of the gas, any substance, equals to 22.4 liter. Assume that 8.50 liters of iodine gas are produced at STP according to the following balanced equation. How many grams of potassium iodide were used? To answer this question, when you see the STP, write 1 mole equals 22.4 liter. STP at 1 atmosphere and 273 Kelvin, this equality is always true. So in this question, if you look at the first line, you'll see that we have 8.50 liters of iodine. So what is given is the volume of iodine, and it is asked for the grams of potassium iodide that were used. So we always start with the given information, 8.50 liter of iodine. Then I can use this conversion to convert the liters to the moles. So liters will cancel out, and then using the balanced equation and stoichiometric ratio of iodine and potassium iodide, I can get the moles of potassium iodide. So for 1 mole of iodine, I used 2 moles of potassium iodide. So now that I have moles of potassium iodide, I can use the molar mass to convert moles to gram of potassium iodide. If you use the periodic table, the molar mass of potassium iodide is 166.00 gram for 1 mole of potassium iodide. So moles will cancel out, and doing the math, it would be 125.98 gram, and to the correct number of sig figs we have 126 grams of potassium iodide. Now we talked about ideal gases and the formulas related to them. Now we want to talk about the real gases, which deviate from the ideal gas law. The ideal gas law, if you remember, the formula for that was PV equals nRT. And this formula is based on two assumptions. First, there is no intermolecular forces between the gas molecules. This situation is obtainable when you have very high temperature. So for that you need high temperature, because at very high temperature molecules are traveling so fast, they are moving so fast, therefore they don't have enough time to build up intermolecular forces between each other. The second requirement is the gases, the particles of the gas have no volumes comparing to the volume of container. So basically their volumes are negligible, and that is obtainable at very low pressure, because at very low pressure, or in the other words, at very high volume, we can ignore the volumes of the gas particles. So these two criteria are required for a gas to follow the ideal gas rule. However, if we decrease the temperature, particles move slower, so they can build up intermolecular forces. Therefore, we add the term N2A over V2 as an adjustment for intermolecular forces to the formula. As you can see in the formula above, this term right here added to as an adjustment for intermolecular forces. Also, at very high pressure, the molecules, the volume of the gas molecules is not negligible anymore. So the term NB, as you can see in the formula above, subtracted from the ideal gas formula, then correction for molecular volume. So these two criteria are for real gases, and these two criteria are for ideal gases. So remember, at low temperature and high pressure, we have deviation from ideal gas law, and we need to do some correction to the actual ideal gas formula.